Alright. Anyway, there we go. Alright, so, sorry if you didn't rely on the movie, it came out rather poorly. So, you can hear what I'm saying very clearly, you can see me moving around, you can see absolutely nothing I've written on the board. So, that's a lower, so hopefully this will be a better angle and that might actually make it work. Alright, so how many of you would say that you are really familiar with logarithms? And it's like totally obvious to you how they work. There we go. That's exactly what I expected. I did. So in the notes, to go like totally like I'm even older than I am, I talk about slide rules. Yeah, exactly. So not in my day, but in my parents' day, they use slide rules to do all this stuff, and slide rules are based on logarithms. And so if you understood how a slide rule worked, you would totally have this like intuition for logarithms that we have completely lost. But logarithms are really, really cool, and they do lots of powerful things. And we need them today to start talking about dimensions. So I want to quickly remind you, and this is the first time you've ever seen it, how a logarithm works. Okay, so you may have memorized this funny formula. So the natural logarithm of x, you may remember what its derivative is?
1 over x.
Yeah. Which doesn't mean much except that. Okay, this is a more tricky one. If I remember that derivative. Yes. It's the same thing times the logarithm of 2. The logarithm of the thing that it's got up front. Okay? So what do you think this one is based on that?
Yes, log.
10 dx log 10. And then our favorite, what's that one? Yeah. Well, why is it e to the x? Isn't it the same as this rule? It is. But we can write it this funny way where it's actually e to the x log of e. Because log of e is 1. So this is one of the lessons is why is the natural log a special one? It's a special one because it's the one that has to do with e. It's the inverse of e in some sense. You can take the log of e to the x and you get x. Or if you take e to the log of x, you get x, right? So it's like the inverse operator of exponentiation. That's one way to understand it. But this is also kind of a nice way to expand. So it's a special thing that when you take the derivative, you get the same thing back. Other neighboring things, raising them to the power x, you get this correction factor. And in this case, this correction factor, I'm putting this on the notes, is about 2.302. And this correction factor is about 0.6931. So if this thing that's being raised to the power has a log that's bigger than 1, it's kind of a big number in log space. So whereas this one is a small number because it's multiplied by something, the leftover bit is something smaller than 1. Does that make sense to everybody? And so this is the one where it's exactly 1. So it's like tipping a balance. This correction factor has got to make this a little bigger, and this correction factor has got to make this formula a little bit smaller, and this is the one right where it's balanced in the middle. Okay, so that's one of the magical properties of log. But you may have also seen log base 2, which looks like that one, except instead of e to the x, it does the same thing with 2 to the x, or log base 10 and the x equals x. Everybody seen those before? Or sort of in some dimly lit cobweb filled corner of the brain? Yeah, okay. So there's a lot of beautiful things you can do with these. One of the things you can do is when you plot a logarithm, a semi-log plot. So if I had something that goes like, and I plot it, what does that look like? It goes up, right? But if I make this a logarithmic axis, right, and I plot e to the x up here, what does it look like? Looks like a straight line. So this is one of the other really powerful things for log, is that if you have something that's an exponential, if you put a semi-log axis on, it will make it easier to read. That's one powerful thing. If I do a log-log axis, log in both directions, then everything that is a power law, so like, like a Taylor series or a geometric series, like this kind of thing, comes out to be straight lines. And the slope of the line is the power to which the largest thing is raised. So this is kind of the graphing world of logs. But there's one last piece that I want to talk about logs, which is really important for what we're doing today, and it's also why I put the logs in the linear chapter, which is that logs turn multiplication into addition. So today we're going to want to talk a lot about formulas that are something like this, where maybe I have 3 factors, and I'm going to think about making them into combinations like this, where A is raised to some A power, B is raised to some B power, C is raised to some C power, and they're multiplied together. And this is a nice way to write things because frequently we have like quantities that are like this. So let me see, what's an example? So the acceleration due to gravity, right? Is something, so this is the distance over a time that you accelerate due to gravity. And it looks kind of like this. It's got a factor g to the first power, it's got a factor of time to the second power, and it's got a number out front. But we frequently end up with combinations that look like this. In fact, almost all of our calculations that we would ever do for a physical problem, each term in the solution is going to look like this. Okay? Well, we just spent all this time last week talking about linear systems, and this is definitely not a linear system. But it can be if you take the log first. So the log of f and c is just the log, the whole thing. But if you work on this property for a while, the log of the product is the log of the sum. And in fact, so if that's true, what do you think raising to a power does? It multiplies it. All right. So proven that by just saying log of A to the A is equal to log of A plus log of A plus A times log of A, right? If A was an integer, I could have done it that way. So why is this form handy? It's much easier to solve because what kind of operator is this? It's a linear operator. So now we've taken something that was, it's not linear in B, because log is definitely not linear, but it's linear in log of B. And it's linear in log of A, and linear in log of C. So if we take the log of all variables, we've taken something that was a multiplication and turned it into something that's an addition. If you think about this for a while, this is why these graphs also work. I took something that was a multiplication, a curvy curve, an exponential, and turned it into a straight line. Took something that was a power law, so a multiplication of different powers of x, and turned it into a straight line because now it's becoming a linear operation with those different powers of x, or powers of log of x. Okay? So, we will come back more times to using the log, and there's going to be one homework problem, which if you use the log is much, much easier. So this is a really nice thing to do if you're thinking of an approximation, which is like a change of something, at least the first order. So if I was thinking of the change in x as y varies, I can just think of that as a delta x, so displacement in x. And so delta x, so the delta of log of x goes like the delta of x over x. So it's essentially partial differentiation, but what it means is if I'm interested in how much x changes relative to its size with the change in y, taking the derivative of the log of x is a really helpful thing to do. Because the derivative of x is just the change in x, the absolute change. This is the change in x scaled by x itself. So if x changes by 0.1 in whatever units, this isn't very helpful. But if x changes by 1%, this is really helpful. Because if I set this to be 1% of this, so this whole side is 0.01, I can find that out if I do a formula for x by taking the log of it first. So we'll just put it out there that this is one of the pieces of manipulation that will be helpful for the homework. Okay. All right. So, all right, so we've been messing around a lot with math, kind of straight math, just reminding ourselves how to solve equations and things, but we haven't really started to link up to physical processes yet. And so, or geophysical processes. So today we're going to start talking about dimensions of units, which is kind of maybe the most sensible thing. So let's use a climate change analogy. All right, if I tell you that sea level rise at the end of the century is going to be 100, what would you say? 100 what? Right. It really matters, right? If it's 100 meters, it's a big problem. If it's 100 centimeters, it's still a big problem. Actually, a pretty accurate estimate of the problem we are really handling. If it's 100 millimeters, maybe it's not so big of a problem. If it's 100 nanometers, it's definitely not a So the units matter, but the units matter not only in what measurements, but the units matter in the way that we construct equations. So this form, the reason why I wrote this out like this was, this is kind of the way that you would build if you wanted to write down what sea level depended on, what would you think about? What are some things that sea level does depend on? Temperature of the ocean. So when the ocean gets warmer, it expands. So global mean sea level in some general one would have something that looks like temperature. Would it be temperature to the first power, temperature to the second power, temperature to the 10th power? We have to know something pretty sophisticated to figure that out, right? What are the units of this? And what are the dimensions of this? This is the one we just talked about, so. What is global mean sea level measured at? A length, like it's a height, essentially. A height, technically it's a height above a particular reference level, but it doesn't matter. It doesn't matter what it is, it matters that it's a height. So we could say this is a length scale, and then over here on this side of the equation, we have something that's, what's temperature measured in? Temperature units. So Kelvin, Fahrenheit, Rankine, whatever you want, with some kind of temperature unit, which I like to use theta to distinguish it from time. So we have this funny notation, or kind of useful notation, where you might use a square bracket, which means what are the dimensions of this thing. So the square bracket of dimensions of this would be equal to L, and the square bracket of dimensions of this would be equal to theta. Okay, so what's missing in this equation? Something like an expansion coefficient, right? So I could put a number in here. Let's just say the expansion coefficient is 2. It's not, but anyway. Is that equation okay? Why not? Units don't match up. So why is it important that the units match up? If I change this from centimeters to meters, but keep this in Kelvin, what happens? Yeah, it doesn't work, right? So if I say that the temperature rise is 1.5 degrees Kelvin, I need to somehow know to change the coefficient. The coefficient had better have units in it. And so I don't know what that coefficient is, but I can, what do the units have to be? To make this part of it work out right. Length over temperature, somehow. Right? Length over temperature. So this thing had better have something, sound like degrees C, meters per degree C, whatever it is. So here I'm writing the dimensions, and here I'm writing it with units, just to be concrete, but really I shouldn't have written it with units with the square brackets. Yes. So a unit is like meters, centimeters, that kind of thing. A dimension is more general, so all measures of length have dimensions of length. It doesn't matter which particular units whether you're using furlongs or meters. Just, it's a unit of length, okay? All right, so that's one thing we better check. So every time we have an equation, it had better have the same units on both sides of the equation, right? We already hinted at one other thing that it better have the same on both sides of the equation, but we didn't even dwell on it last week. If I had a matrix on one side, and a matrix on the other side, What was I supposed to have checked?
The number of rows composing the columns.
So they should be the same. So the one I've drawn here is terrible. That's definitely not right. They should have been the same size. So the number of rows needs to be equal and the number of columns needs to be equal on each side. Because each one of those is an equation, right? So if we wrote it as 3x plus 2y plus z equals 5, because of the pluses, this is only a 1 by 1 and this is a 1 by 1. But when we wrote it as a matrix, we would have written 3, 2, 1, x, y, z. So 3 by 1 times a 1 by 3, which is still a 1 by 1. So we should have been counting to make sure that we had the same number of equations. It would have been crazy. I couldn't have even, well, I don't even know how to write it. 3x plus 2y, and then also z equals 5. Doesn't make sense, right? I would need to do something like this if I wanted to say that kind of a statement. Does that make sense? So this is one thing, every time we have an equation, it needs to have something that's balanced on both sides in terms of the matrix size. It also needs to be balanced on both sides in terms of the units and dimensions. Okay? Because if it isn't, we're gonna get messed up. Like if we change our units of length, but not our units of temperature, our whole life is gonna fall apart. Okay? All right, so we will do more sophisticated versions of that, but want to make one kind of, so one other trick we did last time, which I didn't, I sort of commented on. Oh, I could do it here too. I'll leave that one in. So if I have an equation, whatever, well, I'll take that equation. If I have that equation, I could multiply this by a mess of different things, as long as they are equal to what? 1. I can multiply by lots of fancy versions of 1. So one fancy version, and I don't see why it would be helpful right now, I can multiply by that if I wanted to. That might be algebraically convenient. I can multiply it by I over I, which some of the complex homeworks were helpful that way, or frequently it was more like I plus 1 over I plus 1, so that you would cancel, you would take the complex conjugate in the denominator, and that would simplify the way that the complex numbers were working. If this were a matrix equation, I could multiply it times a matrix times the matrix inverse, the identity matrix, which is an even fancier version of 1. It's a big version of 1, but it's still an identity. So, and we saw this one came into play when we were talking about diagonalization of the where we had that C matrix and we multiplied by C times C inverse right in the middle, and so we multiplied by a very fancy version of the identity matrix. What's the important thing in terms of units that I might want? So we had this conversation about over here about this being, what if this is in meters? How do I write that in terms of centimeters if I choose to switch? What's a fancy kind of one that's really useful for converting from meters to centimeters? 1 times 10 to the negative 2, but with units, because that's not equal to 1. But I could definitely multiply by 10 to the negative 2 centimeters. I gotta get it right. 10 to the negative 2. I can't do it. 100 centimeters. 1 meter. That's 1, right? That's a fancy way of writing 1. But what does it allow me to do? Now I can cancel the units of meters, and then I would be able to write 200 centimeters per degree C. So just like it was convenient at other times to multiply by a fancy version of 1 to convert from complex numbers to different complex numbers, just like it could be convenient to multiply by a matrix times its inverse, multiplying by an object like this is a really useful thing to do. So let's think about that for a second, because this actually tells us something semi-deep. That's the same as this, right? Does this equation have matching dimensions? Careful, dimensions, not units. So it's, what's the dimensions of this side? And the dimensions of this side? Units, meters, centimeters. You actually can write a true equation whose units do not match. You cannot write a true equation whose dimensions do not match. You cannot say any unit of temperature equals any unit of length. That doesn't make sense. But you can say that 1 meter is the equivalent of 100 centimeters. Okay? Or, even more interesting than this, you could say 1 depth of the ocean is equal to 3.7 kilometers. And so this is a practical unit that you might want to build your problem off of. You might be thinking about the depth going from 0% to 100% of the depth of the ocean. So that might really be the convenient unit. And so to write it this way, so here the dimensions don't necessarily match. The dimension over here is the dimension of the ocean. The dimension over here is kilometers. Oh, sorry, I just said that wrong. The unit over here is units of the ocean. The unit over here is kilometers. The dimensions are length in both cases. Everybody on board with that? This seems sort of, I know this seems sort of silly, and we should, but it's like, these things, now I want to do something that's really, I want to step up to the next level of thinking about this. I want to make sure we're clear on these pieces. Okay. So, what if I take a physical equation, and the one that I chose for the notes is a nice partial differential equation, which has lots of funny symbols in it, which don't really matter too much, except we're going to think about what they mean a little. This is the horizontal momentum equation for a fluid. So this is a big, complicated, nasty thing. It's a nonlinear partial differential equation. It's a big kind of a mess. But can we appreciate the units of it and the dimensions of it without even understanding the equation? Because I think that there's some things that are hiding here that we might like to think about, even if we don't try and solve the equation. And in the old days, before people had computers, they would have looked at this equation and said, there's nothing we can do. This equation is too hard. This cannot be solved. And now with computers, we can solve it approximately, but we still can't study it generally unless we use really powerful mathematical methods. We don't even know, actually, there's $1 million prize that if you can prove that this class of equations, the fluid dynamics equations, have a unique solution, you get $1 million. We still don't know that the fluid dynamics dynamical equations have that property. So that's, you know, the level of how hard these equations are in some sense. But from the perspective of units and dimensions, we can make progress. So this is a velocity, this is the horizontal velocity. So what are the units and dimensions of a velocity? So the dimensions of u would be length over time, and we might write that in meters per second or whatever units we prefer. So what's the units of the derivative of velocity? Length over time squared. So the t downstairs behaves like a fraction, which is why this Leibniz notation for derivatives is great, because you can forget about it from the perspective of taking units. So t has the units of time. And so this one has the units of length. We can think of this having the units of velocity over time, or we could think of it as a length over time squared. That's this term. Okay, what about this term? I'm adding them together. So if I can add two things together, do they have to have the same units? Or just the same dimensions? They definitely have to have the same dimensions, and they sort of have to have the same units, because you have to convert the units before you can add them together. So if I can say 1 meter plus 1 centimeter, that makes sense, but I can immediately convert into either meters or centimeters to add them together. I'm not gonna carry that irrational fraction or whatever. What's that they call the fractions that they don't? Whatever, I don't know. But anyway, I would think it's 101 centimeters or 1.01 meters. I would convert it one way or the other. But so from the perspective of dimensions, this term had better have dimensions of what? Length over time squared, right? Because otherwise it wouldn't make any sense to add it together. How does it have units of length over time squared? Because there's now two velocities and a length. This has to be an L, right? So L squared, these two together give you an L squared over T squared. This one gives you a 1 over L. So on that we get L over T squared. Everybody see that? And then this one, now we have a different velocity in a different direction. It also has to have the same dimensions as the velocity in this direction, which is something we'll get to in a little while. But we know that this whole term is going to have what dimensions? L over T squared. And so now sometimes it's convenient to give different directions, different magnitudes of, we might think that the u velocity was a big one and the v velocity was a little one. So we might actually introduce a different L, like an L in this direction versus an L in that direction. I'm not going to do that now because that isn't helpful for the simple part, but you can do that, which is kind of like playing games in your units just to keep track of things. So instead of calling this L over T squared, I could say there's a y direction which is narrow and an x direction which is long, and so I make Lx, which is big, and then Ly, which is small, and I could keep those without canceling them, and that might be helpful later. Okay, this is the Coriolis term. So this is something that's related to the rotation speed of the Earth. It's a frequency. It's actually twice the pendulum period, the Foucault pendulum period. So it's like, it's 2 pi, 2 times 2 pi over 24 hours. Equals there. At the North Pole. So time Okay, that's a weird object. What are its dimensions? So does pi have dimensions? Yeah, it's just a number. It's a fancy number, isn't it? Does the sine of latitude have dimensions? Doesn't actually. It's an arc length. It is actually a fraction. So sometimes you might say that you could think about gradients and radians and all of that stuff. We don't have to worry about that now, but doesn't have any dimensions. So the only dimension here is this part. So f has the dimensions of what? 1 over time. So then what are even if we didn't know that, assuming this original equation was correct, I could have figured out what their units were, because what do the dimensions of this term have to be? L over t squared. Okay. And we can keep doing this. This obviously also has to have L over t squared. This has to have L over t squared, so we don't have to do that again. But there's some funny objects in here that have weird dimensions. Like, what are the dimensions of pressure? What's the dimension of viscosity? What's the dimension of density? So we can do a next step and do something that's really kind of a cool trick, which will make it a little easier to think about that. If I pull out the dimensions, length over time squared from this, and make this guy dimensionless, put a little prime on it. So I'm now defining a new time, which is equal to whatever my unit time is, times my old time. Oops, there we go. And I'm defining a new length, which when I multiply by whatever my units of length are, I'll get my old length. So this one is length without dimension. It's the ratio of the physical length to whatever our dimension is. So this seems a little weird. Let's think about it in the context of this equation that I wrote before. If I was measuring length in terms of like distance across the Pacific, and you told me I want 1,000 kilometers, and I say, well, the Pacific is 10,000 kilometers, this length would be 1/10. It would be 1/10 of the way across. So pulling out the relevant unit from the problem simplifies our life, because now this thing doesn't have any dimensions, because they're all absorbed into this ratio. So does everybody see that if I do this and I define those things, that I'm going to get whatever my L and T are decided to be, they're going to come out front, and I'll get the primes in here. Everybody see that? And the same thing will happen with this term. I would get L over T squared, and all these would become primes. Everybody on board with that? Okay. And I would end up with an L over T here, L's over T there. So every term has an L over T squared, so I can just divide through by L over T squared and see if it simplifies my life. Everybody follow what I'm doing? This is where it gets interesting. So what's the L over T of this guy? If I pull out the L over T factor, it's going to be L over T times U prime. Then I've got F hanging over here, and then I divided through by L over T squared, so I've got T squared over L, cancel, 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 F T. So what's FT? What are its dimensions and units? dimensionless. Because I have 1 per time times my unit of time, whatever my unit of time is. Okay. And I can keep going. And I get a funny one on this one, which is going to be equals minus mu plus 1 over e where du is defined to be L R from to be okay. And this one, I'll call this thing Frosty. Oh, sorry, don't even know. Okay. So what are all these crazy things that I've written in here? What can we say about their dimensions? They have to be dimensionless. Why do they have to be dimensionless? Because we've already subtracted the dimensions out of this term, so it's dimensionless. U prime is also dimensionless, so the thing in here has got to be dimensionless to make this consistent. It's a little more complicated to make sure that this is dimensionless, this thing has to be dimensionless, this is dimensionless, this thing has to be dimensionless. So all of these are dimensionless quantities. Okay? And they have these funny two-digit names because they're typically named after people. So this is the Rossby number, which is named after Carl Gustav Rossby. This is the Euler number, named after Leonard Euler. This is the Reynolds number, named after Osborne Reynolds. And each of them, there's no reason why. I mean, I could have just as well defined the inverse of this. Like, there's nothing special about that, except somebody's already written it down that way. And they said, hey, this is a dimensionless unit, which is kind of interesting for the problem they're working on. And sometimes they're actually multiply defined, but the same thing appears with different names on it. They're not necessarily unique. But there are conventions about this, and the important thing is that they're dimensionless. Okay. So, why is it important to write this equation in a dimensionless form? What does it tell us?
It tells you the ratio of the importance of different quantities.
It does, because it doesn't matter what my units are. If I know how big the Rossby number is, I know how big that term is. Right? There's no difference. We were talking about at the beginning, you said sea level in meters, sea level in centimeters. This number has no more, there is no more dependence on units. It's all dropped out. So once I calculate this number, it is just a number. So if this is 0.1 in meters per second units, it's also 0.1 in CGS units, it's also 0.1 in ergs and feet pounds of torque. It's also 0.1 in whatever you want, whatever obscure system of units you want. So that part is dropped out. This equation, this dimensionless equation, will be the same regardless of the choice of units, which is cool. It also, there's something more powerful. So what if I manage in the laboratory, we were talking about the Pacific before, but what if I manage to build a laboratory system that has the same Rossby number, the same Euler number, and the same Reynolds number, but in a little tiny scale, like a scale model? Can it be the case that that scale model would behave differently from the Pacific? because we removed the dimensions from the problem. So our miniature Pacific model, if I got all of these dimensionless numbers to be the same, would be identical physically to the full-size model. In practice, that's usually not possible because you'd have to make the viscosity much, much lower for the smaller model, and the viscosity of water is already pretty low. So we don't really we can't actually do that frequently, but some of them we could. Does that make sense? So that's called dynamical similitude. And so, which means you have the same dynamics, but you have a scale model instead of the full thing. And it's a scale model not just in volume, it's a scale model matching these things, right? So sometimes it might make sense, like when you rescale a problem, not everything would scale, I used to get frustrated. Do you guys ever get the sponges that they would say 100 times bigger when soaked in water? These used to be in the back of colored books and things that they would sell you something and they would be like, it gets 100 times bigger, and you would imagine it was like an inch and it would be really big, but they meant 100 times bigger in volume, which was not much bigger because it's only the cube root of 100. Anyway, the way that you scale to make a model have the same dynamics as the big system is by matching these numbers. That's what it means to be dynamically similar. Okay, if these numbers don't change in different units, suppose one of them is really small, like 1 over Reynolds number is a really small number, which is typical for the Pacific. So suppose this is 10 to the minus 9, which might be typical for the Pacific. And this one is 0.1. What would you say is the relative importance of this term versus this term? This term's gotta be more important if this thing is about the same size as this thing. Okay? So that if is big. So remember, how did we get those other things? We said u prime was equal to L over T times u prime was equal to u. And x prime equals x. So looking at these kind of manipulations, how big is u prime likely to be if I made a good choice of how big L and T are? So if L and T are actually the right size for the problem I have in mind, how big is u prime going to be? Let's get an example. If I'm measuring velocity and I say the Pacific is 10,000 kilometers, and the time scale is the time scale that it takes for a current to cross the Pacific, which is order of years, then L and T would make, even though u is a small number, like 2 centimeters per second, u prime would be about 1, because the current I'm thinking of is the current that goes the whole distance L in the time t of interest. Like, that's how I would pick L and T. They'd be the length of interest and the time of interest. Similarly, the x size I'm thinking about is about the size of L. So x prime has got to be about 1. So this thing, if I did it right, should be about the size of 1. And this thing should be about the size of 1. So now, what we said before, that this term is probably more important than this term, holds. Because the things that have been made dimensionless are probably about size of 1. So we're going to come back to this next time. The only last piece I want to say is we could just throw this term away if it's small all the time. And then we could simplify what we have left over. So next time we're going to talk about a systematic way of doing this. It's going to exploit our logarithm expansion, making it into a linear system of equations. And we're gonna talk about how you can throw away terms or keep terms and what the consequences are. And we'll be able to do that even without knowing the underlying equation, which is even cooler. So, all right. Thank you, everybody. I'll post this video and see whether it's any better. Probably not.